Hello, good morning. In the last video, I had discussed about the transition probability and Einstein coefficient, that what information they contain. And in this video, I will discuss about the relation between the Einstein coefficient and what the concept basically you can conclude. And here, important point is, as you know, that in laser stimulated emission transition basically dominates over the spontaneous emission, and this is one of the important concept, right, which we use. So relation between Einstein coefficient, for that what is our assumption? My assumption is that there are two states, one is E1 and second is E2. These are two different states, correspond to the ground state and excited state. The number of atoms here are considered N1 and N2 respectively. So this is the primary assumption, and as you know that here large number N1 plus N2 is equal to N0. N0 are the total number of atoms. These are total number of atoms which are distributed in the E1 energy state and E2 energy state, right? So the first step in the relationship of it that comes through the probability transition probability, you can say, or transition rate. That means basically number of atoms they transit from one state to the other in per unit time. For an example, you can say that there are two states, E1 and E2. These are N1 number of atoms, these are N2 number of atoms into the excited state at a particular time. So if I have to find out the probability of transition from E1 to E2, that how many number of atoms are approaching to the excited state, then it is defined by this way: N1 P12. P12 for the one atom, as you have seen into the last video, and here N1 P12. N1 is multiplied by the P12. That means total number of atoms which are absorbing the energy and going into the excited state. So N1 P12 is equal to N1 P12 U nu. Here the early told this is Einstein coefficient, and this is the energy density which is required to excite the atom, right, in terms of the U, function of frequency. Now from E2 to the E1, N2 P21. So in the next is that these excited atoms are the number of N2. So how many number of atoms are coming into the ground state spontaneously and by stimulated emission process? So those are combined here, as you can see. So N2 P21 is equal to N2 A21. This is case of spontaneous emission and this is case of stimulated emission. So total transition probability is defined by this way: N2 P21 is equal to N2 A21 plus N2 B21 and this union. So take out common here this N2, and as a result you will get this A21 plus B21 union. So this is our second equation, right? So this was the first step, and here the next step is this one, that is about the thermal equilibrium. So what will happen here at this time when you talk about the thermal equilibrium of a system? So then that time actually the transition probability from ground state to the excited state and excited state to the ground state will be equal. This is the important point. So at this temperature, which is called the thermal temperature, equilibrium temperature, at this temperature these two transition probability will same. So now what will be the result? Result is, you can see here, this N1 B12 U nu is equal to N2 A21 plus B21 U nu, right? This is simplified way, and now further simplification by taking U nu term common, right? So you can put by this way: N1 B12 U nu minus N2 B21 U nu is equal to, and rest of the term this one. Now you can take out common U nu from here, and rest of the term is this, is equal to N2 A21. Now you can find out for this u nu is equal to N2A21 upon this one. Now take out this common, the whole term N2B21, and as a result you will get this u nu is equal to N2A21 upon, this is common, so N1B12 upon N2B21, this is the result, minus 1. And further simplification, N2 cancel out, you can write in this way A21 upon B21 into 1 upon this vector as it is, and 1 upon N2 ratio, and this is B12 upon B21 ratio, so you can say that this is equation number 3, right? And further you can see that E1 and D2 the energy states, right, for this process which we are calculating the Einstein coefficient. And here one of the important point, if they are fixed, it means the energy level will and lifetime of those energy states will be fixed, so there is no change. So in case of excited state, we consider here B12 is equal to B21. The meaning of taking equal these two different coefficient is this one, because the characteristics of these energy level remain same. And when we put B12 is equal to B21 in the last equation, so that becomes equal to 1, and in this ratio we observe only one term, right, that is N1 upon N2. So this is equation number 4, right? So next step, this is the third step. In this step what we are doing, basically we are just implementing the Boltzmann's law, that basically we use for the distribution of atoms in different energy states. So this law basically says that number of atoms correspond to the energy states. N naught is the total number of atoms, K is the Boltzmann constant, and T is the temperature. So by using this, N is number of atoms at a particular time in a particular energy state corresponding to this energy state. Right, so by using it for the energy state 1 and for the energy state E2, right, so you can see here N1 is equal to N naught, the total number of atoms, N1 are the number of atoms correspond to the ground state, that is E1, B, K, B, Boltzmann constant, and temperature. Similarly, we can write for N2 are the number of atoms in excited state, and this expression. So by using it, one can find out the ratio between N1 and N2, that is E raised power E2 minus E1 upon KBT, where you know that KB is the this E2 minus E1 is equal to delta E. So from this relation you know that delta E, E2 minus E1 is equal to H nu, right? The difference between these two energy level is correspond to the emitted photon, H nu. So instead of delta E, one can write the H nu. So I am putting this value here. So this N1 upon N2 becomes e raised power H nu upon KT. Right, here K is the Boltzmann constant, as I have already told you. Now putting this value, so I am substituting this value here, right? That was the ratio of N1 upon N2. So this becomes equation number 5, you can say, or 4.1 A21 B21 upon this. And now this was the third step, and now this is the fourth step. At fourth step, what you have to do, you have to just compare this equation with the Planck's black body radiation formula, right? That is basically u nu is equal to 8 pi h nu cube upon c cube into 1 upon e raised power h nu upon kt minus 1. Compare these two equations, this one and this one, you will get this A21 B21 ratio, that is equal to 8 pi h nu cube upon c cube. So by comparing these two equations, the rest of the terms are same, this one and this one, so you will get only these 8 pi h nu cube upon c cube. So here in the left hand side you see, observe only these two constant A21 B21, and out of these 8 pi h c are constants, and nu is the frequency. As you know that if there are two states E1 and E2, and you have determine already delta E is equal to E2 minus E1 is equal to H nu, or further you can say nu is equal to E2 minus E1 upon H. Here H is constant, right? So this is only H. So this nu directly depends on delta E. So you can say nu is directly proportional to the delta E. Delta E means this E2 minus E1. So see, observe this result. This ratio A21 upon B21 is directly proportional to the nu cube. What is it means? This is the important part here in the Einstein coefficient. As you know that B21 is related to the stimulated emission, right? And A21 is related to the spontaneous emission. So in laser basically, these two coefficients represent the spontaneous emission and the stimulated emission, and this ratio is directly proportional to the energy gap. So in laser, what is our requirement? Our requirement is that stimulated emission dominates. So if this stimulated emission dominates over the spontaneous emission, what should be the result of the energy gap? So how much energy gap we have to fix? That basically contain the information of nu. So if B21 we have to we want that this B21 dominate, so it means the nu cube, this result will be smaller, right? This nu should be smaller. So energy gap between E2 and E1 should be reasonable according to the output of laser. So we have to check that point. So E2 and B21 contains actually that information, right? This was related to the Einstein coefficient. And further, if you have any question, so you can ask a related question, or if you have any doubt, you can also suggest any topic for the discussion. And please press the bell icon which is near to the subscription tab. So thanks for watching this video. If I'm asking again, if you have any question, related question, you can ask.